All right, good evening. Good evening, everyone. It's good to be back again this wonderful Wednesday evening. If you can hear me, just give me a thumb up or just a wave. If you can hear me, just give me a wave. How's our week been? Good evening, good evening. If I'm audible, can you kindly just wave? Oh, fantastic. Joy, good evening. Charles, good evening. Ogechuku, good evening. Praise, good evening. Bola Dale, good evening. Elizabeth, good evening. Razak, Yetunde Vivian, yeah, good evening. Good evening. It's good to be back this evening. All right. So today we'll be looking at performance evaluation, metrics for assessing model effectiveness. Like I've always said in this class, it's not just enough for you and I to build models, but our models must be what? Effective. And how do we test the effectiveness, or let's put it, how do we test the performance of our model if there are no what? Metrics. If there are no metrics, it's just like students going to school and there's no evaluation metrics, or you're just going to school, no tests, no assessment, no group work or group activities. Then how do you test? How do we measure? How do we measure that the student is performing above average or below average, or performing excellently well? So the same thing for our AI/ML models. All right, everyone, good evening. I can see you, Eddie, Ibilola, Smart, Anthony, Two Arts, Aduragbemi. I can see you, Ibrahim. All right, so quickly we'll run through our slides for today. Okay, so these are the evaluation metrics that we'll be looking at. We'll be looking at a confusion matrix. We'll be talking about even the classes under the confusion matrix. You have your sensitivity, you have your specificity, precision, accuracy. You have your AUROC, that is your area under the ROC curve, and your F1 score. These are the things we'll be looking at today. Well, because we're actually working on a classification model, and our projects will be starting very soon. This time next week, I'll be talking more on our projects and what we need to do. Like I've said since last week, I said by now you should have a problem statement. You should know the real life model or project that you want to, real world situation that you think you can solve, and you should have put out what are the features that are necessary for me to solve this. Then you should have gotten your data set ready. So I think you should be ready for the project, because we're actually almost getting to the end of this course. Because after this, the next 3 weeks, then we'll be talking about a project and mentorship. So I believe, so I think our platform is open now. The LMS is working fine, so you can reach out. Then I think tomorrow evening also I'll create a discussion so that we can actually talk. All right. So these are the matrices we'll be looking at today. Okay. So when you talk about your confusion matrix, this is what your confusion matrix is actually about. It talks about a prediction on the actual class and the predicted class. So what is the actual outcome that you're expecting versus the prediction results that you have gotten? And you can see from the left hand side, you have the positive, the negative, then that is the y-axis, then the x-axis, you can see your positive and negative. So when you have your P against P, it talks about what true positive. Then when you have your P against this, it tells you what you are talking about, what your false positive. Sorry, that should not have moved. All right. Also, when you're talking about your positive with negative, you're talking about your false negative, your negative negative, true negative. Then you can see you have your sensitivity, which is your true positive divided by your true positive plus your what? Plus your false negative. So we'll be understanding. So this is what your confusion matrix. Confusion matrix is just giving you an overall map, or let me call it an heat map, an overall heat map that is telling you, okay, these are the actual prediction that you, or these are the features that you have. It shows you your number of features, and it tells you, okay, these are the predicted classes. Then you cannot relate it to the actual classes. Is it correct or it's not? So that is it. So as we go further now, you begin to get more light on this. So I just wanted you to sensitize your mind with this image. So anytime you're talking of confusion matrix, it's talking about what the overall prediction of your classes. All right. Exactly. So I talked about it, confusion matrix. You have your actual class, that is the classification that's been made by what the clinician. I'm talking about the health data now, that you and Mr. Blessing, you are working on. It could be your weather forecaster, but based on the practical that you have been taking. So I'm using that for the confusion matrix. Then when you talk about predicted class, it now tells you the classification. What's happening? Was it fast? Sorry about that. It talks about the classification made by the machine learning algorithm or your model. All right. So like I've explained, so this is your actual class. That is the expected outcome based on what the clinician has actually predicted. Then can our machine also give us this prediction better, faster, cleaner? So that's just the essence, just comparing. So when it becomes when the problem starts is that when this is outperforming this, then there's a problem, because now you have trained a machine to do that. So you should be able to do it faster, more accurately, more more organized. So anything here must be superseded here. Everything here, whatever is gotten here, by the time you are predicting here, it should actually give you a better performance than this. All right. So that's just your confusion matrix. Okay. So let's talk about the nodes. I told us you have the TP, the true negative, the false negative. So when you talk about true positive, when you talk about your true positive, you're talking about instances that are actual positives and what predicted to be positive. So if you can see my example below, actual, the patient has diabetes, and you have predicted, your machine learning algorithm, your model has predicted that what truly those set of patients have diabetes. So it means that what it's a true positive. Exactly. It means that it's true. Being positive, it is true. So it's just as simple as that. Like we always say, anything AI, ML, both our programming environment and everything, it's just pure English. It's just pure English. So instances that are actually positive are predicted to be positive. All right. This mail is a spam mail, and your machine learning algorithm predicts that what is a spam mail. All right. You have created a weather forecast. What's it called? Model. All right. The weather analyst says rain is going to fall by 12 midnight today. Your model also says what? Rain is going to rain by what? By 12 midnight today. So it means that what that is a true positive. All right. Then you now look at the false positive. When do you say it is false positive? Note also that the false positive is also called the type 1 error. False positive. Instances that are actually negative and they are predicted to be what? To be positive. You see that is disastrous. Imagine somebody going to a clinician or a medical practitioner, the MP, and he or she does not have diabetes, and he or she has been diagnosed of having diabetes. Naturally, there's a problem already. The person begins to panic, and so that's why your model must perform to the optimum and what to optimum value. So it becomes an error when a machine where there are instances that are actually negative and your model or your algorithm is predicting it to be true when it's supposed to be what? To be negative. So that's why we call it false positive. Your system is saying it's positive, whereas it is not positive. So the example says what? Actual, the patient does not have diabetes, but the algorithm is predicting to say the patient what has diabetes. So it becomes exactly. It's a threat alert in cyber. Okay, yes, exactly. So you can see. So you know that's cyber security might be. So that's just good. Should be further. So that's a very good one. That's a very good one, Prof. All right. So we've been able to know the difference now between a true positive and a false positive. For a true positive, the instances are what? Are true, are said to be true. There's a disease, a condition, and the machine learning is saying, yes, I concur, there's a disease condition. Then false positive, there's no disease condition, but what the machine learning is saying, what? There is what? A disease condition. Ibilola, fantastic. It is what? Misclassification. You are very correct. Misclassification. So your model needs to be what? To be evaluated. So and that's the reason why we are doing that. So that we don't create models that are generating fictitious outcome. And this can this can just destroy a whole lot of things. I saw an article yesterday that was retracted, and it was so painful. As beautiful as the article was, but they were doctoring their figures. They doctored some of the figures just because they wanted to publish in a high ranking journal facility, and they doctored. And most of these journal publishing journal houses, most of the times when they notice, oh, why are people actually, people are citing this one, they can call for you and tell you, send in your data and the methodology that you used. And that was what happened to them. They told them to send in the data. There was delay when I was reading why they had to retract. There was delay. Eventually, they sent the data. What are the methodology? They sent the methodology under the same condition. The journal or publishing house carried out the same experiment and realized that what the metrics that were actually reported have been doctored. In fact, they were far beyond what in fact, issue of misclassification, issue of so you have to be very careful. You have to be very careful. We are in Africa, and we say everything goes and you can go away with things. But when it comes to the Western world, you need to be very careful. These are things that their licenses are being seized for. Your patency is being denied, and it might take you years again for you to regain your integrity. So that's why you have to be very, very careful when you are classifying or building a model. All right. Then the next talking about false negative. You can see that we have false positive and also false negative. These are places whereby there are conditions that are positive, but your machine learning algorithm is saying no, it is negative. That is the type 2 error. So you need to note the false positive is a type 1 error. The false negative is called the type 2 error. So those are the kind of two types of error that you usually found out in an algorithm that has not been properly taking time to be corrected. It causes a lot of problem. So you see instances that are positive and predicted to be negative. Somebody has come, he has diabetes. Just imagine a clinician or an MP telling the person he doesn't have diabetes, and the person gets so excited and calls his friend and say, let's go and celebrate. And they buy bucket ice cream and bucket chicken and everything. And they are, celebrating. Whereas he has diabetes. They have caused problem. So just imagine the model also doing the same thing. We are talking about models being more accurate even than human being. Stripped of error. Timely. Exactly. Colade is a problem. Yes, it's a problem. It calls everybody and say, I've been scared of diabetes. I don't have diabetes. Oh yeah, his friend will say, okay, let's go and buy bucket KFC chicken bucket. Oh yeah, go to this place and buy ice cream. Let's celebrate. Then with 2 bottles of red wine. Before he knows it, under a month, there's multiple complications and the patient dies. You know that that is a huge problem. So our system also must not give such report. Stephen, good evening. I can see you. Welcome. All right. Then you have true negatives. True negatives. Joy is laughing. It's true. So true negatives. True negative, yes, the instances are negative, and your machine algorithm has predicted that they are negative. So you find out that when you are looking at the best way your machine learning algorithm or your model should perform is that what it must classify true positive and what true negative. If there's no disease, it should say there's what there's a disease. If there's no disease, it should tell you there's no disease. And if there are diseases, it should clearly specify that what their disease, their condition. So we need to be very, very careful. And that's the essence of what metrics, performance evaluation. We need matrices to what? To be able to carry out performance. And these are the best of them. Your coefficient matrix, which embeds both your precision, your accuracy, your specificity, sensitivity, and every other one is always very fantastic. So in fact, it just gives you a lot of ease. So you immediately before you start publishing or deploying or releasing, you can see, oh no, this my model is not classing very well. This my model has not adopted the right way of classification. So maybe you need to retrain, or maybe the way you have cleaned your data. You see, I keep on mentioning data, and somebody was talking to me about 2 days ago and said, why do you like talking about data set? I've realized that one of the first problem you face while your model is not carrying out the actual classification starts from your data preparation, your data cleaning, handling of errors, mitigating every error, and that's what we call data pre-processing. You must make sure that to the best of your knowledge, exactly, you are correct. You are very correct. When the machine works, that's Ezechi, Emmanuel, exactly. Why the correct is what? So it's supposed to be negative. So you are very, very correct when you talk about false positive. So that's just it. You are very correct. You're very correct. So we need to watch out anytime. You are not instances are also referred to as observations. Yes. When you hear me say instances, I talk about observation. Yes. So there are terminologies when we talk exactly. If we're carrying out a lab experiment now, we'll talk about what observation, but I call them instances exactly when it comes to AI ML. All right. Okay. So now let's look at it now. There's you have type 2. Look at the class discussion. I say which is better, false positive or false negative? The false positive is what? It's a type 1 error. When we say somebody has no cancer and you say the person what? Has cancer. Then you talk about a false negative. The person has cancer and the prediction says the person has no cancer. Good evening, Temitope. Good evening, Omosola. Yeah, good evening. Good evening. All right. So what do you think? I just want us to have a discussion. I'll put my... Thank you very much, Prof. Thank you so much. Thank you so much. Okay. I don't just want you to put type 1. I don't just want you to put type 1 or false positive. You must give me reason. I want to be sure so we can discuss. You must give me a reason why you are telling me it is type 1. Okay. Elizabeth said none. They can both cause bigger problems. All right. All right. Let's see those that said type 1, type 2. Okay. Greta says neither. That is good. That is good. Let's see type 2 error. Type 2 error, Philip. None. But if it's to choose one, so type 1 is still better. Based on your human thoughts, right? Okay. Okay, let's see. Somebody say none. Okay, I can see a lot of none. Benjamin, Godwin, Cosiso. Okay, Joy. All right. Somebody still said false positive. Say FP is a misclassification, which is better than what? FN. Okay, I love that idea. Say false negative can kill someone. So you are very right. Everybody is correct to an extent, but if we are to choose anyway, if we are to choose based on risk, but the risk of both are still high. Imagine somebody who is hypertensive already, and you say the person does not have cancer, and you say the person has cancer, and the person in that place has an hypertensive episode, and dies. So both are very, very what? Very dangerous. But on the mild, if you want to be mild, thank you, Samson. The two are misleading. I love that. Very misleading. Very misleading. Say type 2 error is better. It carry less risk. You say actually the person has a cancer. You said somebody has cancer, you say does not have cancer. Then they go and buy a bottle of Coke and say, let's celebrate. So if we look at it very well, misclassification is just not it at all. When it comes to anything that has to do with what's it called? With classification. Any error, classification error at all, it puts danger. Okay. I love that. I love Isaac. So the reason I say one is better is because type 1 error we need for that test. Okay. Yes, that's a very good one. That's a very good one. That's a very good one. But Bola Dale, I love that. Oguntunde says what? Misclassification is what? Is deadly. It's deadly. So somebody say when the person dies from hypertension, the cancer didn't kill him. So it is still a false. Excuse me. But the decision of the classification or whatever diagnosis has been given led to what? That hypertension that he would have survived. But because he or she thought that what they have. So the basic line is that what? Misclassification is not what? It's not good. So none is good, especially when it has to come to what? Health. We have been using health data set to teach. In fact, okay, maybe for something like weather forecast, it might still be a bit okay. As forecast and say, okay, rain is going to fall by 12 midnight today, and it doesn't fall. I don't think there's an arm done. Then I say, oh, rain is not going to it's not going to rain. Then it rains. It's still quite okay. It's still quite okay. But when it comes to what? Health data or health itself, now you are dealing with life. So when it has to do with life, exactly. So all of them are bad. Both of them, both. All of the above. There's none. So misclassification is not good. It's not good for health prediction. All right. I love what you guys have done. That's the reason why I always love for us to do a bit of a discussion, pause and talk. So I can see things. In fact, I've seen people, the way some of you have analyzed, I love that. One thing I've learned is that in life, when it has to come to things like this, most of the time, there's not always a wrong or right answer. Even if there's a right answer, if you have an answer and you can defend that answer with evidences, then it's always good. So it allows you to search the in-depth of your heart and think in another manner, so you think of it. And I've loved what everyone have done this evening. Eddie says, if it rains, my Owambe can scatter. Eddie, that word is for Owambe now. So I think, how do you prevent that? Maybe next time you just prepare your mind and say, okay, we won't do it under canopy, we'll get it all. In health, misclassification is just too dangerous. So that's the conclusion. In health, misclassification is what is dangerous. It's dangerous. All right, thank you everyone. I really love this. We have a lot of type 2 cases in radiology. Type 1 is majorly caused by physical diagnosis. Yes, you are very right, sir. Mr. Shegun Bello, you are very right. Because of human error could come in. Yes, human error could come into that, and that's why we are building models that will help. And that's why when we talk about things like this, and some of our radiologists and clinicians get upset and say, they are taking our jobs away, and I made them know. I'm happy that Some of those radiologists now are joining our data science course. There's Datican, there's a data science for medical imaging in Nigeria, which I'm one of. I'm affiliated with them, and we have radiologists and MPs now joining us. Those tools just help you. It eases you, so it helps your work faster. You work faster. You can diagnose faster. So, like I tell people, AI and ML has not come to take your jobs away, but those who embrace those tools are the ones that will take our jobs or their jobs away. So it's just as simple as that. But the tool itself is a wonderful innovation that's come, and it has to stay. It has to stay. Exactly. Misclassification also in finance is very, very dangerous. Thank you very much, Eniola. I really appreciate that very much, sir. Yes, sir. Just imagine there's been a fraudulent activity, and your model is saying no, there's no fraudulent activity, and before you know it, within overnight, billions of naira has been, or billions of dollars have been moved away from the company's account. So that is just it. So like jam that switch from technical glitches to human error. You will see, yes, we say the confusion matrix as an evaluation is a sector and industry specific. No, you can use a confusion matrix for all. It's not just for health, but because we are working on health data set, so that's why I'm giving that example. So it's not just for health alone. Also in aviation, exactly. Thank you, Praise. Thank you. So you can see misclassification anywhere will always crop up an issue. And if you are not careful, some are life-threatening, some are resources, resources are being wasted. Just imagine building a model of over $30,000 or £30,000, and it's misclassifying. Or look at the NASA, what's it called? The NASA geospace model that helps what's it called? That helps these aviation guys to, just imagine somebody who is going to the moon. Then the model is misclassifying the geographical point where they should land. It means the person can get lost in space. So that's just very, very good. So you can see those are the things. So these models, machine learning models, AI models, they are fantastic. They've come to ease us, but we must be careful to undo errors as much as possible. All right. So how do we introduce this into our models? Do we create a feature that takes care of this? Yes. There's when you are doing this, there's a formula in your Python environment which you are going to be working on this week. Mr. Blessing is going to be teaching you how to call what's it called? Evaluation libraries. So you have the evaluation libraries. You can select which of the evaluation module you want to use. So it is there. So don't bother yourself. By Friday, you are good to go light. You are good to go. I just want you to know the concept behind it, so that you just understand so that you can read. By the time you read your confusion matrix, it comes like a box, which aligns. You have your y and x axis, and it gives you your number of features, and it tells you where are the true positives, where are the true negatives. Then it gives you the number of misclassification also. So it gives you your misclassification. I'm sorry, I wanted to add it to these slides. I don't know how I missed that out. So on our group, I'm going to create a group on our LMS. We'll talk about it. Then I'll push a configuration matrix graph so that we'll see that. So misclassifying data carries several risks, primarily related to security. Yes. Thank you very much. Thank you. Is it possible in automobile also? It depends on what area of Oluwole Stephen. It depends on area of automobile you are looking at. Which area are you talking of? This automatic like those self-driving system and things like that. I think it can work in that area also. If it's not well classified, how do you tell the system, or how do you build a model for automobile that lets the model knows when to hit the brake in case of things like that? So you have to be careful also. Have to be careful. Nearest to object, what is the meter? Maybe the meter for it to brake automatically is maybe between 2 to 3 meters. and mistakenly you classify to make a what, how would I call it, a meter or so, and you find out that they are accidents. So it's possible. It's possible. It's possible. Thank you very much, automatic braking system. So I really appreciate you guys. Okay, so I think it's been a wonderful discussion. So let's move on. All right. So the next thing we are going to be looking at is what is called sensitivity. Sensitivity. What's sensitivity? It measures the proportion of actual positive cases that are correctly identified by your model. It measures it measures it to make you know what are the proportion of those areas that have been actually classified rightly. Classified rightly. All right. Something is missing in my slides, and hold on, please. Wow. All my the formulas are missing, which is very surprising. I can see them in my notes here. I don't know what's happening to that. All right. Maybe I will need to update or re-upload. So just give me a few minutes. Let me re-upload the slides again, because you need to see those formulas. All right. Let's just take about 2 minutes off, then I'll be back. Let me try and upload. So while we are uploading, while I'm re-uploading, I can ask the questions again. So please, let's just quickly, let me re-upload the slide. I can't, because I want us to make sure as possible that you can see the slides. All right. So sorry about that. Let's try again. Okay. It should come up in a few minutes. In archaeology, this could also lead to yes, automobile diagnosis and things like that. So you guys are very, very, very correct. When is it best? I think it's when is best? I believe when it has to do with classification, I think it's always best to just confusion matrix gives you insight into what your model has actually performed. So I believe I usually tell people every time as much as possible, especially when you are working on numerical data sets, where there can be some errors and things. Admin, can you help me put up my slide? Thank you. I've corrected the errors in the slide. Thank you very much. So let's see. We have, I'm still having the error. Sorry, I'm still having that error. So I think maybe it's the way it's being projected. So let's not bother. So sensitivity, proportion of actual positive cases that are correctly identified by the model. Abraham, I think I've answered you. So I've told you it's in all situations of your classification, I think it's best when you are doing anything that has to do with classification between binary, mostly binary classification. Also multiple classification, some people use confusion metrics, but when it has to come to binary, exactly, you want to know between one order, is it false, is it positive? It's always good to use your confusion matrix. So as I was talking about sensitivity, it measures what the proportion of actual positive cases that are correctly identified by your model. Exactly. So it looks at your model after classification, looking at it to say, okay, what you can see, I put a line. So it's measuring what? It's measuring this line. You can see PP versus what? PN. All right. So you see it is talking about what? Across this line. So you have your what? Your true positive divided by your true positive plus false negative. So the outcome you get will make you know, is my model sensitive enough to pick? So it helps you. On the later, Christopher has said something. All right. So let's go on. Maybe your project is, it seems. Okay. All right. Yes. So that's TP divided by what? TP plus FN. So the number of true positive plus your number of true positive divided by the addition of your true positive and your false negative. So it tells you, okay, what proportion the actual positive cases. So if you maybe you have about 300 positive cases, and your model can pick about, maybe you have divided, okay, 300 is 100%, and your model can actually correctly pick about 80%, then you're yes. So it means that your model is sensitive. So it's just like the English was sensitive to what? To classifying correctly the proportion that are what? That are truly positive. So it's just to calculate the proportion. So it's just what this sensitivity does is that it just adds more insight to your classification itself. So it gives you more insight to say, okay, yes, there has been a proper classification. Then when by the time it begins to drop and you're having about 40% and so, then you know that something is wrong. There's been an issue of what? Misclassification somewhere. All right. Someone is saying compatibility issue. Maybe I might just need to share my screen so that you can see the slides. But when we go on break, so let's just manage for now, since we have 15 minutes left before the break. So when we come back, also I can reiterate so that we don't keep switching screen. All right, so that's what sensitivity talks about. Then you have what you call the specificity. I said it measures the proportion of actual negative. So you can see now when it's sensitive, it's sensitive to what? Correct what? To correct a classification. Then this specificity also wants to know how many actual negatives that were correctly identified by your model, because that's how you can weigh. You can weigh the proportion. You've gotten 2 data sets that says diabetes and non-diabetes, or patients close to about 10,000 records or 100,000 of records. So you want to be very sure for those that are not diabetic or that have no cancer. You want to be sure that your model can pick them. So that's specificity. So it's being specific to what? To picking what? Negatives. Then sensitivity is sensitive to pick what? Cases that are positive. So they're just what? Opposite and yes. So if you look at that, I forgot to tell you, sensitivity can also be called recall. Exactly. Because most of the times I've seen somebody doing a classification and he said he did sensitivity and he did recall. Sensitivity and recall are the same thing. So most time when you see people's model and they say recall also can be called sensitivity. So it's called, you can use it, you can call it recall, or you can call it but most of the times when we are working on numeric data set, we use recall. Then when we are working more on images, we say sensitivity. So it's just, but they are doing the same thing. Both recall and sensitivity is doing the same thing. Sensitivity is measuring as my system be able to pick actual positive cases based on what? On the data set that has been given. Then the other one, specificity is talking about what? And you being able to, your model being able to what? To pick what? The actual negatives based on what? On the prediction model and the data set that you have been fed. So you see it now, you see that their formulas are almost the same. For sensitivity, you have true positive divided by the summation of true positive and false negative. Then when it comes to, yes, somebody say recall is common. Yes, recall, you are very right. Recall is. Then when it comes to, thank you, Oluwole Stephen, for the formula. Then when it comes to specificity, you can see true negative divided by what? The summation of true negative and what? False positive. So you can see that they are word and opposite. So one measures on positive. Have my system be able to pick all the actual positives. Then as the model be able to pick what's the actual negative. That is you're talking about your specificity. All right. Okay. All right. Then you look at precision. So there's also precision. Exactly. You know, your model must be precise. In fact, it must be accurate. So I say it measures what? the proportion of positive cases that were actually positive. So you can see it's almost close to sensitivity. Sensitivity is speaking what the actual, everything has been said to be actual. Can it peak then? But when it comes to precision, this one is measuring that, okay, the predicted, can we look at the predicted positive cases that are predicted in comparison with the actual cases that have been said to be positive? So we're looking at what proportion of the actual that has been done by the clinician as your model being able to pick out, as your model being able to actually work on and be sure that yes, okay, this model is actually classifying very well. And that's why you find out that precision is always in percentages. For all of them, it's better they are in percentages. You just multiply by 100, whatever you get. So it helps you to validate and evaluate your system. So when your precision is going below 70, then something is wrong. In fact, from 70 is just too small. So I tell people, let's pick it from 85, then maybe to 90, 93, 94. That's the fantastic. That's the fantastic. So you need to put that in mind. So that is what? True positive divided by what? The summation of true positive and what? False positive. Exactly. So the opposite of your precision is negative predictive value. But most of the time we don't need that, because when we already know the positive, we can now look at, okay, what was your data proportion? From that you can pick your negative from it. So we don't usually use your negative predictive value. Most of the time it's not really reliable for anything. We already know that they are negative, but we want to be sure, because you are working on diagnosis, somebody wants to come and use your system that's been deployed to take a result or a picture of his or her blood or chest X-ray or the metrics that has been given and enter into your system to be sure to say, okay, if I put it into this system, well, self-help system. Just imagine us going to hospitals now where you are waiting for your what's it called? Maybe the doctor has said go for a test, and you've gone for a test, and we have self-help systems that have been deployed like this. Maybe there's just a doctor around for that day, and the doctor has about 100 patients to see. All you just do is take a technician and say, go and use the self-help system that's been built. So the person takes his result, just scans it, the system scans it, and your model picks it up and runs quickly to be sure, based on this result that you've been given, no, okay, you are not diabetic, but I think you are moving on almost to, it tells you, it does suggestion also. So that's why when you build models also, models should not just only predict or classify. It should be able to, especially when it comes, in fact, all your models should be able to give suggestions, relate suggestions and say, based on this, your result, I believe you should do this, And that's why we love models that are give personalized outcomes. Personalized outcomes. When I talk of personalized outcomes, based on whatever result it has given, it can offer what? Can offer insights. Exactly. You should be able to offer insights. And that's why when you talk about the issue of interpretability, you see people talking of things like GradCam. Exactly. So you see things like GradCam, you see things like explainable AI. Exactly. So not just only to predict, not just only to deploy the model, it should be able to also give what? Thank you very much, Prof. Recommend remedies. Thank you. I love that. Thank you. That's the word I was looking for. Thank you so much, Prof. So there must be a recommendation. Any system you build must give a recommendation. Like the last system I built, and where it was based on a best model. So I put a recommendation that after the training has been done using the data that's been given, I validated with an extra data set. It must give reason why it is choosing out of the four algorithms that I've used. It must tell us why all. It can tell us why all the models are performed the way they performed. Recommend the best method to use, and say, okay, give you suggestions, recommendations. So it's good. So Benjamin says, can precision be like the glucose monitoring armband that makes a suggestion? Yes, it's something, All these things have been deployed, so it's part of what has been put in. But these are measure, when I'm precision, when I'm talking of precision now, I'm talking about a measure of what, of evaluating what your model. So now when it now gives an accurate result, then you can say your what, your glucose monitoring armband is what, is precise. It's giving a precise answer, or precise result. All right. So, but when you talk of precision itself, what, it's a evaluation metrics. It's an evaluation metrics. All right. So let's take one more before our break. Accuracy. In fact, this is the one we shouldn't play with at all when it has to come to accuracy. Accuracy measures the overall proportion of correct precisions, that is both positive and negative, out of the total number of cases. Yes, you want to be sure now. So that's your accuracy. You have a true positive and you have true negatives. So your accuracy now measures between. Thank you very much, Paul. Accuracy score. Thank you so much. So that's just it. You want to know between those things, out of those actual cases that are true and false. Has my system been able to actually pick a higher proportion of them? So has it been able to detect them when it's making its a classification or its prediction? So you have to be very careful here. Last time I was talking about underfitting and overfitting. So you need to be very careful also. When your model is too simple, you have a underfitting, whereby it predicts accuracy will be so low. Then when your model is too complex, again, you have what you call overfitting. Then just imagine, I've told us, no matter how fantastic your models, no model can be 100% accurate. No human being can be 100% accurate unless you're a Carnot engine. Carnot engine was proposed by that German engineer. Can't remember his first name, something Carnot. I was talking about a situation whereby machines and engines can work in 100%, but it was just taught in physics. It was never accepted. There will always be means of error. You have to give what? You have to give quota for error. There will always be error, because even the machine or the algorithm that you are modeling, thank you very much, it doesn't exist. Thank you very much. It doesn't exist. It was just a mere, what should I call it? What it cannot do. Cannot just give its observation. Even though it was adopted into physics, but it was not used. Thank you. You give tolerance. You give tolerance. It says 100% accuracy is perfect, but impractical. Thank you so much. Very impracticable in real life sense. It's not possible. It's not possible. Even doctors will tell you, as far as they are medics and they have gone, doctor will tell you that sometimes they do what? They do trial and error. Even when your result come out, and that's why you find out that if 6 of us visit a medical practitioner and we say we have malaria, he will prescribe 6 different types of malaria medicine to all of us based on our symptom, based on what he feels like. So he's like, no, this person, the level of his temperature and things like, oh no, he needs this kind of malaria drug and things like that. So human direct algorithm also make a mistake. Exactly. You just give, thank you. That's the word I'm looking for. Daniel Salahu, postulation. That's it. You still remember your physics. Thank you so much. Postulation, it was just a mere postulation. No engine or machine can be 100%. And that's why when we are talking of AI models, when you start building your model, you will see me giving you comments. All right. Giving you comments. So attendance soon in 3 minutes time. In 3 minutes time, we'll go for, it's 7:57 now here. So in 3 minutes time, we'll go for break. So it gave me a postulation. So when you start building your models, you see me, I'll be giving you comments, because we'll be working together with everyone. We are all working together. When you send me, I see your accuracy, I will tell you, okay, based on this, your accuracy and the script you sent to me, go and do this, go and do that. You'll be wondering, why is he saying so? Because most of the time, thank you, science is progressive. One day we'll get to being perfect. Are you sure? I think only God can be perfect. Only God. Man can just move towards perfection, yes, but I'm not sure. You still make error. Have you not been in situations where you say, I won't tell lies today? It is between 0 to 1. Thank you very much. And you say, I won't tell lies today. And immediately you are proposing in your mind that you won't tell lies. Somebody will come up to you and all of a sudden you will tell the biggest lie you ever told in your life. In fact, when you go yourself, you say, you will marvel and wow, did that just come out from my mouth? So there's no idea. Thank you very much. Thank you very much, Innocent. Thank you. Thank you. Yes, you can. That's, but we don't use accuracy alone. That's why I'm teaching you every matrices. Based on those matrices, now you now combine them to look at their average and look at it. So you can't use one matrix, you know. Accuracy alone, and you will have a model that is very accurate, 95%, but the precision is poor. And you know, you can be accurate and you are not precise. And you can be accurate and precise. I hope you are getting it now. Aha. So even saying I won't tell lies is a lie. Yes, yes, there's no ideal accuracy. Error is common. Yes. Yeah, so that's it. So my model can be accurate and it's not precise. And somebody's model will have a lower accuracy than yours. Maybe yours is 90 and your precision is 75. And somebody has a model of 85 accuracy and 90% precision. I'll pick that model because that model fits very well. It will work better than your model if tested by external data sets. Then the different modified, okay. So that's just it. So you see, these things are also measures of life. So you know, because it is human being that has programmed these models also. So we are using measures of life also. Are you precise as when you give information? Is your information always precise? Are you accurate about the things you do and things like that? I think my slide has a mind of its own. All right, no problem. So let's go for attendance break. It's 8 already. So let's go for attendance break. During that period of our attendance break, I'll use that to share my screen so that, or go and check like Oluwole has told me to look at the compatibility that I use in saving my slides. So I'll do that and change it then. We can all work together. Claiming to be perfect is a type 2 error. Yes. Misclassification. Exactly. Situation in imbalanced classes. Thank you so much. Thank you so much, Antonio Okon. I love this. So let's go for a break. Admin, can we go for a break? Thank you. Okay. So while we wait for, okay, thank you. All right. All right, welcome back, everyone. Yeah, so it's good to be back. So I'll just do a quick recap of what we've done. Then we'll go on. So I'm sharing my screen now. So I think this will be fantastic. So let's go on quickly. All right. So we've been able to look at confusion metrics, spoken about sensitivity, specificity, precision, and accuracy. Exactly. So I just gave us when we started the class, we started with the map of the confusion metrics map, and we spoke about what confusion metrics does. It tries to compare the actual class. When we talk about actual classes, classification that has been made by clinician versus what the predicted classification made by your machine learning algorithm. So it tries to look at them. If 100 classes have been made by the clinician, then your machine learning should be able to predict up to 90 to 95 of that. And if it does the 100, then it's also fantastic. So you should be able to do it faster, more accurately, with precision. Exactly. All right. Then we looked at the terms in or your confusion matrix. When you talk about true positive, we're talking about what the instances that are positive and that have been predicted to be positive. So the individual has diabetes, your machine learning says it's true, the individual actually has what diabetes. Then we looked at false false positive instances that are actually negative, but the machine has predicted them to be what? To be positive, and we call them the type 1 error, which we actually discussed, the type 1 error. So the person or the patient has no diabetes, but the model says he or she has diabetes. Then we look at the false negative instances that are positive, but have been said to be negative. So they are false, which takes us to type 2 error. The patient or individual has diabetes, but the model is saying he or she has no diabetes. All right. Then we went to true negative. We spoke about instances that are actually negative, and the system has been able to predict that what they are truly negative based on what the clinician's record, also the actual prediction class. So that is always very good. It has no, a patient has no diabetes. Your model or algorithm also says what? No diabetes. All right. Then we now spoke, we talked about the class, what's it called? Discussion, which is better between the type 1 error and the type 2 error. And in conclusion, we're able to say what? Misclassification is what? Is a menace. So we shouldn't pick one error above the other. So we should just try as much as possible to avoid what? Misclassification. All right. Then we spoke about sensitivity before we left, and that was the formula I was talking about here, where you have your true positive divided by what? The summation of your true positive and false negative, meaning that what? Your system is sensitive to measure what? The proportion of what? Actual positive cases. Actual positive cases that your model has identified. Exactly. So it's more of that. And I said the opposite of that is your sensitivity. Why your your specificity. Why sensitivity is concerned about actual positive, specificity is concerned about what? Actual negatives. Actual negatives. Then from there, we went to talking about precision. Is your model precise? What measure, what proportion of predicted cases that were what? Actually positive? As your system precise? And that brought us to that discussion when we ended with accuracy. I said a system can be accurate and not precise. And you have a system that has less accuracy and is much more precise. And I say I will pick that over what? Over any other model. Because accuracy alone itself cannot what? Cannot be used as a measure of what? Of evaluation alone. All right. Okay. I was thinking there's no question, so we are good to go. So that's wonderful. All right. So next We are looking at accuracy shortfall. What are accuracy shortfall exactly? And you know, most especially when you are working with binary classes. I didn't want to talk about, but it's good. I saw somebody spoke about imbalanced data set, and I'm happy I actually put this. As accuracy is a simple and intuitive metric, but it can be misleading when dealing with imbalanced data set. When I saw that person that put that, I was very excited. I'm so happy with you guys. I'm so proud that you guys are learning well and doing very well. And it shows that some of us are doing extra studies, and it's fantastic. So when one class, when you talk of imbalanced data set, one class significantly what outnumbers the other. You have to be very careful. You'll be so surprised that the class with the higher, it will give a very fantastic accuracy, but it's a lie. The classes are not balanced. Then it will give you an accuracy of like 97, and you're wondering, no, it's supposed to what the proportion of what negative versus what the proportion of positive that has been. So why pick one area and leave the other area hanging? And this is where things like handling of class imbalance comes in, using your SMOT analysis. I saw Mr. Blessing teaching you mean, standard deviation. So based on whatever what's it called, algorithm, so you can do that. When it comes to image data set and deep learning data set, we use what I call weighted classes. So a lot of things like that to undo your imbalanced data. So you must make sure you are doing data augmentation. You make sure that the data is balanced. Whatever is on the positive is being balanced. So how do you do that? Maybe you reduce their shape or things like that, or you remove a hair. So your system will actually do that for you. So there's something called downsizing. So that you are downsizing or what? You are upsizing. So these are things that you'll be seeing in your practical classes. So I just had to talk about this. When I saw somebody, I just saw it. I was excited. I said, I put this in my slide. So somebody had already spoken about that, which is very, very good. Exactly, an outlier. I love this, an outlier. So that's good. That's good. So with me, I love what you have done. So that's an outlier. So that's good. That's good. So it shows that we are all doing very, very fine. Somebody is asking me a question. He said, what is the relationship between sensitivity and specificity? All right. So what is their relationship? They are just evaluation performance for your classification model. Actually talking about what a disease versus what not disease, or false versus true. So what do you measure? Sensitivity, as I've told you, measures what? How well your model detects positive. Then specificity tells you how well your model detects negative. Exactly. So what is the focus of sensitivity? You are trying to avoid false negatives. Then in specificity, you are trying to avoid what? False positives. It's just as simple as that. So what happens is that they are actually balancing each other out. One is increasing the other or decreasing the other. So they make sure that what they are balanced, so that a number of what is not more than the other one. So it's giving an actual balance. So that is what is happening there. All right. So let's go on. Then now I go to what we call area under the ROC curve. Exactly. So when you talk about AUC, when anywhere you hear AUC or you see somebody says AUC dash ROC, it's just talking about the area under what the receiver operator characteristic curve. So what is the receiver operating characteristic curve, or what is it plotting? It's plotting what? Your true positive rate, which is your sensitivity, against your what? Specificity at various classification threshold. I hope you are understanding what I'm saying. So what does it measure? It just measures the model's ability to distinguish between positive and negative classes. That's every grammar you have spoken here. Area under ROC curve. It's just telling you how well your model can balance up between what negative and positive classes. So you can see. So this is the area. This is your area under the curve. So you can see the balance there. So anything below here becomes a problem. So this is the cutoff. So you have a balance between what? So it tries to what to balance off from the true positive and the what and the false positive rate. So this is your no discrimination curve, no discrimination line. So which is always 0.05. So everything here is just balancing what the ability of your model to be able to distinguish and balance between this positive and what negative class. What this guy helps you to do is that in the problem of when you have like the question of accuracy. So that's why every time I think Mr. Blessing will also tell you this. When you are calling up your evaluation and matrices, it's always good, I tell people, so that to be sure that the accuracy you are getting is meaningful. Always what? Evaluate with AUC also. So your AUC will tell you, your AUC will let you know that that no, your what's it called? Your accuracy is not good. You have to be very. I think that it really helps a lot. Say thank. Okay, it really helps you. It really helps you a lot. Is anybody wanting to ask a question before I go on? I'll just slow down a bit. So when you're having an AUC ROC score that is of between, let me just put between 90 and 100. So it shows that what your model is what is excellent. So even when your accuracy is saying the accuracy is low, your AUC ROC will tell you no, the system is still working fine. So that's why I said it's always good to combine matrices together. You use your accuracy, you use your precision, you use your sensitivity, which is the record, you use your specificity, you use your AUC ROC. So by the time you look at each one of the model and interpret, so you find out okay, even when one model is having a lower accuracy than others, maybe others are at 90, peaking at 90, 91, and it's having 89, but its AUC ROC score is good. It's between 90 and 95. Sensitivity too falls between 90, precision also falls there. Then you now see those that are having accuracy of about 95. Their precision is a bit lower, maybe 85. AUC ROC is 85. Sensitivity is 85. Specificity is 85. Then you begin to wonder what is going on. Exactly. But then the ranges of your AUC ROC score, let me give us the ranges so that we understand better. Anything below 0.5 is a worse model. The model is a nonsense model. Let me just use that word. If your ROC is between 0.5, it's on 0.5 itself, then it's like your model is doing a random guessing. That's what your model is doing. It's doing what you call random guessing. Then from 0.5 to you can put them in percentage. The first one less than 50, the model is worse. 50% on the dot, your model is guessing. 50 to 60%, your model has no discriminative ability. It cannot really distinguish between what's it called, false positive and true positive and true negatives. Then when it's 0.60% to 70%, your model is poor, but it's still better than what a random guessing model, but it's a weak model. But when you have 70 to 80, okay, I can accept that if the performance, if it has an acceptable performance, it's still good. Maybe when I talk about maybe your what's it called, your accuracy is fine, your precision is fine. Okay, you can still do that. But from 80, 90, 90, 95, That's a wonderful one. 80 to 90 is good. Then 90 to 95 is an excellent model. I always tell people, at cap models, when you are at 95, is a fantastic model. When you start talking of models going to 97, 96, 98, I'm always been a bit very careful. I'm always been very careful. To me, it seems that the model is not it's not. So that's just it. That's the way it is. All right. Mhm. Okay. Thank you very much, Francis. I learned from you guys. I stopped using that my earpiece. I'm using my computer speaker. So I tested and I noticed that I think my AirPods are the one giving problem. So thank you guys for your feedback and patience. So yes, Prof, for best practice, it is better to combine evaluation metrics. Yes, you are very right, sir. Very right. So that you can now, you can balance. So, and the good thing is that you can just write a two-line program in your Python after everything has come out to tell you to evaluate and choose the best model for you. So it just makes your life very, very easy. It makes your life easy. So I said your ROC is just your receiver operating characteristic curve. So what is it talking about? Is this curve? Look at this curve that have been highlighted, where there's a cut-off point and a trademark. So anything that falls below, it becomes a problem. You can see 50, you can see where 50 everything here. So you can see anything that falls below here, it's not, the model is not doing well. But anything from here and above, your model is performing. And you see, I say cut off for high performing model, you can see. But everything ranging from where this arc, where there's this intersection upward, from here your model is doing very well. Here is still acceptable as long as it's not below 50, but a bit in here is still a bit acceptable. So that's what it's just talking about. So, but anything here, forget about it. Just forget about it. Your model is not working fine at all. So it's not actually what picking up true positive rate and true and false positive. So you can see it like that. It's not picking them. So you have to be very, very careful. So as Babs have said, it's always good to combine models. Combine models. It's good. So the higher the score, the better the performance. Yes. Francis said no robotic sound. Thank you. All right. Okay. So all right. The model don't overdo. Yes, it's doctored. Thank you. It's becoming doctored model. So I'm glad that we are getting this. All right. So let me go on. All right. Oh, so you should have gotten this. So I've given you values also. So the same value that I explained. So you can see from satisfactory, you can see 60, 65. So you see anything here under this line like this, you're under this area, anything, but everything here like this. So you can see the values and the test quality. So this is on anything from 0.5 to that is unsatisfactory. This is still okay, manageable, but you can carry out hyperparameter tuning. I believe your model should start from what 80% exactly. Anything below, forget about it. There are other people also working on models that needs to. So you need to be very, very careful. You need to be very careful. So that's just it. I just had to add this image for us because I know somebody will ask me what is the level between which. So when you have things like you yourself, when you are doing that, you see, you are shaking your head. No, my model is not. The quality of my model is not. Predictive quality of my model is questionable. Then you begin to walk towards it. Walk towards it. All right. And then the model is also questionable. Thank you. Some argue that let me start from Ubong. Some people argue that okay, your model when it's saying 98 and above is a perfect model, but you know I've told us your model cannot be. Yeah, you yourself you need to go and check. Is there issue with data leaking? Or I've you know there are some ways we want to prove that we know what we are doing and we program what's it called? How do I call it? We program very complex models, and before you know it, your model is overperforming. So you are getting models that are overperforming. So it can be. And most times people argue that okay, it's good, but I will tell you the truth. Mr. Blessing also will tell you the truth. When it comes to the Western world, somebody said I was even planning to create a model that when it comes to the Western world, well, because we've gone for conferences, Mr. Blessing, Mr. Isaac will tell you, when we go for this, and the last conference we had in Mauritius, one of my colleague went and did a presentation. Immediately he brought out his evaluation metrics, and they were seeing 98. I just saw people's hand went up. When they started throwing him questions, I got scared. So that's why it's always good when you have opportunity to have to attend webinars and things. Please don't take them for granted, especially when it has to do with multicultural webinars where people are coming in. Western guys are very, very crazy. Herubong is laughing. Yes, I'm telling you, they gave him. They were just bombarding him. Luckily for me, I was there when he was working with the data set. So when I saw that it was becoming too much, I just told him, can I step in? And I said, if you notice that he said this is a pilot test, taking into cognizance that the data set is imbalanced, then it will get such accuracy. And everybody just started clapping for him. And that was the end. When he saw me, he said, that if he had remembered, I said, that's why I told you. You must be prepared. So I just told them, this is the first pilot testing on this data set. It just got. And the time constraint that we had to actually create that experiment. So he didn't undo class imbalance and some other things. So I told them, I said, so it's possible for the model to give such accuracy. But when he puts that into cognizance and things, then you get what I'm saying. So those are the things you need to look at. So let me look at another question. Okay, let me see who asked another question. Okay, let's see. This thing is running fast. Okay, all right. What's that question? Which regulatory compliance code should we comply with in AI? And I think for now, regulatory compliance, we don't have any compliance in Africa. So I think we are still using the Westerners, the European compliance. So I think during our last session of this class, I'll be talking about, when we start our mentoring, I'll be talking about compliance and ethical considerations. We'll talk about compliance and ethical consideration. Exactly. So it's just what's it called? So those are the things we look at. We'll talk about some of those things. But for Africa for now, is just, let's just leave it that way. I'm not delving into we're still praying for Africa, so I pray. And somebody was asking me, what does the 1 minus specificity mean? It's just a formula. It means that 1 minus what? It's telling you that 1 minus the value of your specificity, which has to do with false positive divided by the summation of your false positive plus your true negative. So that's how to calculate your false positive rate that I was talking about. So there's nothing to it, just 1 minus your specificity. When you do your 1 minus specificity, so if your specificity is 0.95, so if you do 1 minus 0.95, that is 0.05, right? So meaning that 5% of your actual negatives were actually predicted as positive. So these are false positives. Do you get what I'm saying? So we're just trying to look for what's the margin of error. So we minus our specificity by what? By 1. We minus it from 1. We say 1 minus your specificity. We want to know the percentage of the actual negatives that were predicted as positive. So when you get 5% of that, then it means that your system is working very fine. You have 100% of negatives, and you just missed only 5% out of them, and others were well, then it's working very, very fine. But somebody cannot tell me that you have 100. How did you have 100? Sorry. How do you have 100? So you so that's it. So that's why I keep saying you cannot have what? An absolute. Some people will still argue with me and say, no. But so that's just it. Let me see. Okay, no other question then. Let me go on. All right. So let's go. So we have to create, creating compliances. It's a collaborative thing. So I'm just praying that Nigeria will wake up. Yes, you are right. Daniel, you are correct. We'll wake up in Africa and the body of Africa will come together. I know South Africa, Uganda, Kenya, Ghana, Mauritius, and they are working together on an ethical code, which my affiliation is part of. They throw it to Nigeria. They told us the first time they wanted to start that, they came to South Africa, Kenya, Ghana, and Uganda, and Nigeria. Yeah, Uganda and Nigeria. Other people accepted. They say when they came to Nigerian government, they were telling us at the conference there that Nigeria was demanding for money, and that's why they left Nigeria. So it's just 2023 again that they started considering us in Nigeria. So can you imagine? So a lot of things affect these things. We are giants of Africa, but the level of corruption and is just too alarming. It's too alarming. All right, let's go on so that we can finish up our slides and see if we have time for question. Okay, then you have what you call the F1 score. The F1 score. The F1 score is called the harmonic mean. Excuse me, the harmonic mean of your precision and what? And your record, which is your sensitivity. What it does is that it balances what? The precision and record. So what it just provides a single metric that considers both false positives and false negatives. You know that precision is one side, recall or sensitivity is the other side. But now F1 score now combines them together to give like a balance data set. So the F1 score is particularly useful when dealing with imbalanced data sets, where your accuracy can be misleading. For somebody that was asking me then, what are we going to do? Well, what evaluation metric can tell us? Your F1 score will tell you when you are dealing with imbalanced data sets. In fact, you will just see how ridiculous your F1 score will look like. Very ridiculous. And you will know that something is wrong. And every time your F1 score is giving you something very low, it's telling you that what? Your data set is imbalanced. Funny enough, accuracy will do very well. You see 95. Somebody will say, yes, even 98. My model is working fine. Somebody who is good, Mr. Blessing will just go to your F1 score and look at it, and he will just score you X and just say, this person does not know what he's doing. So some people say, no, and I got good accuracy. I kept on saying it. Accuracy is not sufficient enough. Thank you, Abimbola. Thank you so much. I'll get up and take water. All right, I can excuse myself. Thank you, please. Just give me a few minutes. Let me get water. Thank you very much. All right, thank you very much. Thank you. So you can see your F1 score helping us to mitigate that problem. So yes, our country needs saving. We just keep on a lot of wonderful talents in Nigeria, but in fact in Africa. But we just keep on trying. Somebody called me this morning and was ranting. I'm frustrated. I'm frustrated. I'm frustrated. What can an imbalanced data set be? You have negative that maybe your total data set is 5,000. Then negatives are like 3,000, or let's put 4,000. Then your positive are 1,000. The balance is imbalanced. At least they must have the same, the same proportion. Excuse me. So that's just what when you talk of imbalanced data set. I will remind Mr. Blessing to show you an imbalanced data. Right? And that's when when he was teaching us how to plot a class distribution. I was telling you to plot the class distribution of diabetics and non-diabetics. You saw the value and this, and you saw the graph. One was taller than one. Then when he did class imbalance, the two of them became balanced. So I will remind him again to show you guys again how to do that. All right, let's go on. Okay, now another class discussion. Another class discussion now, which is a very good one. Which of the following is the best metric to be used in your report? I want us to think very well. Think very well. I'll give us 2 minutes to brainstorm then. Then if you're answering me, I want to know the reason why. So don't just put sensitivity or precision. Tell me the reason why, or why you have said is one of the best. So it's up for discussion now. Let's do that for the next 3 to 5 minutes. Then we'll go on with our class. So I've been looking at the chat line to see our responses. And if you think, okay, let's go on. Okay. I've said, Eddie, you have done the wrong thing already. You tell me the reason why you are choosing that matrix. Don't just put F1 score. It's a discussion. Tell me the reason why you have chosen this. Great praise. I love that. I love that. I love that. To tell you whether it is balanced or what's not balanced. That's good. That's good. All right. I'm waiting. I'm waiting for our responses. 2-3 minutes. AUC. Okay. All right, Peter. Fantastic. Timilayi and Eddie, tell me why you chose your metrics. I'm still waiting for other people to answer. Where's Isaac? Where's Praise? Where's Babs? Where's Daniel? Okay, Daniel has answered me. Great. Benjamin, good. Okay. 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 All right, Martins. Great. Because it measures the proportion of, okay. Okay, Oluwole Stephen is here. That's okay. So with me, 5. Okay. 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 Praise, okay. Great, great, great. I'm waiting for more people. Okay. Boliwatife 5. You tell me the reason. Can you tell me your reason? Okay. Okay. This is good. Endurance, tell me why you are choosing AUC. Additional, tell me why you are choosing number 5. I want to know your reason. Okay, Oluwayemi, thank you. Grace, thank you. Timilei, that's good. Charles, Prof. Yeah, oh, Eddie, I've seen it. Sorry, Eddie, I've seen your reason. Thank you, I've seen it. Sorry about that. The chat is moving very fast. I've seen it. Great. Great. Okay. Also get a visual representation. Yes, sir. Okay. 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 Light, I'm waiting for your answer. Waiting for your answer. I will say accuracy because as it stands, this data will produce a good model. Okay. Isaac. Oh, this is good. Cost picture. Isaac has picked 2. Okay, that's good. So I love this. I love this. Okay. So with me. Thank you so much. That's good. Boliwatife. Thank you. Thank you. Thank you. Okay. Imabong. Okay. Imeobong. Sorry. Imeobong. Frank. Great. Otunyetunde. Oh, that's fantastic. Issue between. That's fantastic. Sunday, give me your reason, please. Give me your reason. Okay. F1 score. Yeah. Courses sort. Number 5. Tell me why you are picking number 5. All right. So I can see everyone has picked. Abimbola, give me the reason for accuracy. Joy. Fantastic. Fantastic. Okay, we have 1 minute more, then we'll go on. So we can finish our slides. All right. Everyone has done very, very well. If you have chosen AUC, ROC, that's fantastic. But if you remember, when I started, I said it is always good to do what? To have what? Combination of what? Of metrics whenever you want to what? Carry out your performance evaluation. So if you have chosen a single one, is good. But I want us to understand that one metric alone on its own cannot. For those that chose AUC, ROC, yes, AUC, ROC has combined 2 matrices together. But it's always good to add your accuracy and precision. So if you know you are going to be using AUC, ROC, then take your accuracy and precision with your F1 score with that. So everybody, I love what all of you have done. You have done very well with good reasons, fantastic reasons. But I want us to always remember, anytime, make sure you are combining about 3 to 4 matrices together, especially when you are working with very large data sets. If you are working with small data sets, okay, you can still have about 1 or 2. Exactly, Prof. Thank you, Prof. Honestly, there's no single best backup. So I think the question was why we chose one. It's what when it says which are here. Okay, I get you. I get you. All right. Thank you so much, everyone. I really appreciate you guys are fantastic. I see people have said things and I can see you guys giving it back to me in your own words. This is wonderful. You have an understanding of this. I'm telling you, you are good to build complex models that best fit model. Let me not use the word, because when your model is too complex, overfitting. When your model is too simple, underfitting. But when your model is best fit, thank you so much. Anthony, Oluwafemi, Live, Lady, you guys are wonder. Everybody, Isaac, Imelbong, Oluwole, all of you. If I've not mentioned your name, praise everybody. You guys are fantastic. You guys are fantastic. Daniel, Prof, Francis, is just good. But make sure at the back of your mind that anytime I'm doing anything that has to do with evaluation, I must pick what more than one. But like if you pick your accuracy, if you pick this with this, 4 of them, very sufficient enough. Because this guy AUC has already what helped you to explain these 2 guys. So you just take that, you find out that you can easily evaluate your model to what? To the optimum value. So you guys have been wonderful. In fact, since week 3, I've really, really appreciated you guys. And Mr. Blessing told me, he said, you guys are wonderful. He said, when we started, I understood that week 1 and 2 is true. Some of us are just being introduced to new concepts. But Mr. Blessing has given me wonderful testimony about you guys. You guys are doing very well. I appreciate you guys. So And you guys have been making us also to go back and rethink our structure, our techniques of teaching and things. And it's been it's a very wonderful journey. So thank you so much. I appreciate your answers. They're all wonderful. I've told you guys when it comes to ML, AI ML, there's no wrong answer. If you can back it up with a good answer, good analogy, good points, then it's fantastic. Thank you so much. So let's go on. I know I spoke about this last week, but I saw somebody still asking that question. So I just said, let me revisit and we'll use it to end the class. The bias, variance, and trade-off. I know we spoke about it. And I told us that it's a fundamental concept that explains how errors in machines can arise, machine models can arise due to two sources of error. When you have your bias and variance, when your model is too simple, that is what you have high bias, which causes underfitting. Then when your model is too complex, you have high variance, which leads to overfitting. I'm sure we can remember the last class when I was explaining that. Junior, okay, I've already sent the quiz. I'm not sure the quizzes are hard. There are things that you are so familiar with, things that we've done in the class. Nothing outside the box. So I'm sure you guys will do very well. You guys will do very well. All right, so let's go. So that we can spend the remaining 12 minutes to cover up the many. Anyway, we just have about 6 slides left, so I think we have sufficient time. All right, so I went to look for the best model that I can use to explain that to us. So when we are talking about overfitting and underfitting area, and where's the best fit model? So talking about the bias and variance trade-off. So you see anything that falls within this area, we always will generate errors. Anything that falls within that area will always generate errors. Anything that falls within that area will always generate error. Anything that falls within this area we always generate. But when we talk of trade-off is just saying where can you balance the bias and the variance. So in that process of balancing, you can see this curve here. This curve here, within this area, you have your optimal model. And that's why I've said, don't allow your model to be too simple. When I talk about model too simple, maybe even your data set, smaller, very small data set. Then don't allow your model to be too complex. That's why you must know model selection. That's why I talked about best fit model when I was talking about model selection. You must understand the model for the problem you're about to tackle. When should I use a regression model? When should I use a classification model? So because sometimes when you make the mistake and use a model for a data set that has to do with classification, like when you are doing binary classification, you always fall into having high variance or high bias. And there's no way you have the problem of generalization error. What do I mean by generalization error? By the time your data is being tested by external data set, it will not work. Funny enough, your model will be saying, your accuracy is 95, but by the time something else is coming in, there's error for you. There's irreducible error. Your model just fails. It doesn't advance more than this. Look at the optimum level. Your model just remains no matter what you try. So you must be very, very careful. So this line that shows us model complexity, when there's issue on this side, there's underfitting. The model is simple, high variance. There's overfitting. You have high bias. Then you have the issue of generalization error. Your model must fall between. So if we look at the ranges, they range from here. So a model that falls, just like the way I gave you your AUC ROC. So a model that falls within this range from the range of 0.65 to let's make it 0.9 is an optimum model. So that when external data is coming in, it doesn't break out of this region. It doesn't break out of this region. It still tries to maintain optimum balance. And that's why I said it's good to use multiple metrics to check. So it helps you to just balance let it balance. I've seen somebody build a model that 85% accuracy, like I've explained to you, and sensitivity and working very fine, AUC fantastic, and they chose it over a model that having accuracy of 90%, 95, 97%, because it generalizes well. When you bring any external data, the model can still undo it. It doesn't fall short of its performance capacity. So those are the things you just need to look out for. By the time you start your project, you will see you start facing those kind of errors, and questions will start coming in. Then, I already explained these errors to us the last time. Bias, error due to oversimplistic assumption in your learning algorithm. Then when you talk of variance is errors due to model sensitivity to small fluctuations in your training. I've told you your data set and things like that. Then what are your irreducible errors? Noise inherent in data that no model can reduce. Why? Because you have not solved them from your data cleaning area where you're doing your pre-processing. So your model cannot help you. You need to work on them yourself first. Removing what's it called? Missing rows or missing data and things like that. So you need to do those manually yourself in your data cleaning class. Some people call it data cleansing, whatever you call it, pre-processing, data processing. Just make sure that you have done those things. If not, your model will carry them like that, and your model will just keep on running on a particular that line I show you, because it can't work on them itself. If it use it, it can't do it itself. So you need to go back to your data set and correct them. Then don't let your model make assumptions that are too simple. That comes in your coding. That comes through in your coding. So you have to be very, very technical about some of your line codes. And that's why we are telling you use functions. Start with functions and things. Instead of you using a function, then you begin to write something that the function that you can reuse on different, then you begin to write like 20 lines every page you find yourself. Then it gets to a time your algorithm is upset itself. Wow. Why do you have to just keep repeating this? So it doesn't give your model that compatibility. So we need to put that into consideration. Oh wow, 6 minutes more. Let's move. Okay. All right. So we can round off. Okay, so I told us about the trade-off. What do you trade off? For bias, don't let your model be too simple. Variance, don't let it be too complex. Then if it's that, you get underfitting of data, overfits the data. Then you get high training and test error. Then this one, you get low training error and high test error. Then example is what? A linear regression on curve data. You can see it will give you a problem. When you're having a linear regression, you can't use a linear regression for a curve data. What you should be using here is what? A logistic regression. Or maybe a support vector machine. Then using deep neural network on small or noisy data set will give problem. You have small data set, go and use machine learning, go and use a linear regression or something, go and use a small convolutional neural network that you built yourself, just a small few lines of layers, and do that since the data is small. So those are the things you need to look like. You see this one, a complex data model on just small data set. Then mismatch of model on linear is only for every data that like your binary data and things like that. Then you have a curve data set. The person is using a linear regression, then to give problem. Now use a decision tree, SVM, use your random forest and things like that. Then you get a better output. So and that's why I told us now we should have that list of everything now. This is my problem statement. This is the kind of model I want to build. This is how my data is. You must check your data. That's why Mr. Blessing is teaching EDA, cleaning and everything. Know what your data is about. What's the variance of my data, mean, your standard deviation. No, okay, this is the kind of model that fits for it and things like that. So that's why it's called overfitting. The model is too big for the data set. Underfitting, the model is too small for the kind of data set. there will always be problem. There will always be problem. Okay, all right. Then lastly, I think we are getting there. I spoke about how to manage them. I just want to talk about them again because now we are going to those stages of you having to start building your model. So what do you adjust for model complexity? You increase what the model for the bias. For the variance, you reduce what? You decrease your model. Use a simpler model. For training time problem, you train longer when you're having training error. Then for this, you use what we call early stopping, which Mr. Blessing will be talking about, even though we are not using it in that. These are current, this early stopping is always good when you are training images, large number of images. Then for features, add more relevant features when it has to come with a bias, when the bias is high, so that you can reduce your bias. Just pick the features, specific features that you need. Don't use all the features. Then to reduce variance, remove all noisy features, all irrelevant. Then your regularization, which is called the lasso regularization, L1, L2, just decrease. You can use that. That's a means of working on an underfitting model or an overfitting model. Then your data set often has little effect. When it comes to bias, just make sure your model is not is a very good model. So when you are dealing with curved data set, then for your variance, when it's too high, increase your data set. Increase. If you are using a complex, increase the data set. And if not, go and use a simpler model. You cannot increase the data set with then it's a pruning, or use what? A simpler model. When you talk about pruning, when we start talking about deep learning, hopefully, I pray that as things are going on, if there will be another session, maybe I will be able to teach deep learning. Then we'll now be talking about pruning, freezing and unfreezing some nodes in your model. So those are the things you need to do. So finally, if there are any questions for the next 2 minutes, so that then we'll round up for today. Okay. The model chosen for training can contribute. Yes. Praise model choice. That's why I did model selection there. Best fit model. You have to be very, very careful when you are choosing the models. You need to be very careful. You need to know the kind of oh, Faith, thank you so much. Thank you. You're welcome. Yes. I told us it starts getting better. I'm sure the links have been sent now. You will have seen all your slides now from previous slides, all slides that have been uploaded. You'll have seen everything. Then also, I uploaded, Mr. Blessing told me to upload some useful Python codes for you. You want to do normalization, standardization, regularization, EDA, and things like that. He has given me all the Python files. We have uploaded that for you also. So we have come to the end of today's class, spoken about evaluation metrics. So I think everyone now is aware of how to do that. At what point can we know that our data set is properly clean? When you start getting errors, you will get errors, you will know. When you put in your model, it will always give you an error to tell you something is wrong, and it will tell you that it's from your data. You will know. So that's why I told you, study your data set, know the things you need to do in your data. What are this kind of data? What are the cleaning, what's it called? Cleaning, feature cleanings that I need to do, or what features do I need to extract from it? All right, everyone. Thank you for today. You've been all wonderful, Have a blessed night rest. See you next week again. All right. Bye, everyone. Good night. Okay, sorry, before I go, Benjamin, I told you I will start a discussion on the LMS. Then I'll try and start a discussion this weekend, and I'll put some resources for us and some other things that we need to talk about. So we'll have opportunity to discuss the things that we need. All right, good night. Have a good evening. Bye.